Welcome back. We're talking about directed graphical models, and we were looking at this more general sort of example here. We were just playing around with this distribution over 5 random variables. We just started with an arbitrary joint distribution, and we factored it in this way, and we drew some arrows on a graph here that represented each of these different factors. And then we observed that, for example, if x2 was conditionally independent of x3 given x1, then this factor became this, and we could erase this arrow from 2 to 3. And if x2 was conditionally independent of x4 given x1 and x3, then this factor became this, and we could erase this arrow. We could erase the arrow from 2 to 4. And we could go on in this way, applying other, if our distribution satisfied other conditional independence properties, then we might be able to reduce some of these other factors as well and erase more of these arrows. So one thing which is interesting to note, one thing we noticed earlier was that this graph in this simpler case was a graph, and it was also, it was indeed a graph, but it was a directed acyclic graph. It was a DAG, and it was also still a DAG when we had the arrow here. And let's see if this one is also a DAG. So let's think about that. And was it a DAG even before we erased the arrows? So before we erased the arrows, well, let's see. We had arrows going from 1 to 2, 3, 4, and 5, 2 to 3, 4, and 5, 3 to 4 and 5, and 4 to 5. So the arrows were always going downhill. They were always going from higher numbers to lower numbers. So there couldn't be a cycle there, because we would have to start out following the direction of the arrows and get back where we started. But to get back where we started, we would have to go back uphill, and we were always going downhill as we followed the direction of the arrows. So that was sort of an informal argument, but you could make that formal, and you can easily see that in any graph of that sort, you're going to get a directed acyclic graph if we constructed it in the way that we did. Okay, so that was kind of neat, because we were able to start out with a probability distribution and express certain conditional independence properties in a graph. But what if we start out with a graph? Can we go the other direction? What if we have, let's say we have a graph. What can we do? Can we get a probability distribution, or maybe at least sort of a class of probability distributions? So let's start out. Let's just make up a graph here. So let's just draw some. Let's put it over here this time, maybe. So let's put 1, 2, 3, 4, 5, and 6, something like that. Let's make 1 go to 2, 1 go to 3, I guess 3 to 4, 2 to 4, and 2 to 5, and 4 to 6. How about that? So that's a DAG, because so I was trying to keep it. I was trying to make it so that it had that same property, that the arrows only went from lower numbers to higher numbers. Did I said downhill before? I was thinking of 1 as being larger. So I was thinking sort of in reverse there, I guess. But downhill in the sense that you're starting from lower numbers and going to higher numbers. That's a very strange sense to think of downhill. But so we're going from lower numbers to higher numbers. So we're always going, I guess I should have said uphill. So we're always going uphill. And now what can we get a distribution from this? Well, let's see. Let's write down, this has 6 random variables, so it's x1 to x6. And let's see. So first, well, nothing points to 1, so we have the probability of x1. And then what points to 2? Only 1 points to 2, so let's do this. So 1 points to 2. Probability of x2 given x1. I'm just sort of following the same rules that we used to construct the graph, but in reverse. I'm looking at the graph and writing down a factor that arises from that graph. And then the next one, so 3, 1 points to 3. Probability of x3 given x1. So we have this one here. And then 4, 2 and 3 point to 4. So we have probability of x4 given x2 and x3. And then we have 5. 2 goes to 5. Probability of 5 given x2. And one more, let's make it red. Probability of x6 given x4. So, oh, wait, did I miss? I missed one. 3 goes to, oh, I didn't color it. That's what I did. I didn't color this one. I'm just doing, so the colors aren't really a standard thing. I'm just doing them so you can associate the particular edges with a particular factor. And I could also color that 4 there to associate it with that. And so one thing to note is that for each of these factors, there's one vertex in the graph. Like this first factor corresponds to vertex 1, and this factor corresponds to vertex 2. So you could also associate the vertices with factors. So that was kind of cool, right? So we were able to do this in reverse also. Now, of course, this doesn't fully specify a probability distribution. I mean, you still have to say what p of x1 is and what p of x2 given x1 is for all the possible values of x2 and x1, and so on and so forth. So this certainly doesn't define a probability distribution, but it specifies, it characterizes sort of certain properties that the distribution must have. Because not every distribution is going to be able to factor in this way. Okay, so that was sort of thinking, just playing around with graphs and distributions. And now, next we're going to start to get a little more formal. So I'm going to stop there in this video, I think. And in the next video, we'll start to get a little more formal. We'll define some notation, and we'll give a little bit more formal definition of what we mean by a directed graphical model. Okay, see you soon.